Hunting from the air is one of the most complex feats that evolution has produced. Navigating a three-dimensional world while trying to capture prey that has equally impressive escape tactics is no simple task. When we think of aerial predators, we often imagine fierce birds of prey like the peregrine falcon. They sometimes dive past their prey and then swoop up from below to snatch the victim in mid-air. However, some studies have shown the overall hunting success rate of the peregrine falcon is 23.1%. Other aerial predators like hawks, which pick individual prey from a flock, have a similar success rate of 22.5%. Species like owls hunt by pinning their prey to the ground, and although they lack highly developed aerial hunting techniques, they still achieve a success rate of about 25%. Other top predators on Earth rarely surpass this figure. Lions are successful in less than 30% of their hunts. African wild dogs are perhaps the best terrestrial predators, with a success rate of over 70% when working together. But that number still pales in comparison to a predator that isn't very impressive on the ground. To find this predator, you have to turn your attention to a much smaller creature. They hover near bodies of water with stunning wings and large compound eyes. This is the dragonfly. The dragonfly's hunting success rate is an astonishing figure. It's nearly 100%. Dragonflies belong to one of the oldest insect orders, Odonata, which has existed for nearly 320 million years. Their presence in the fossil record is relatively complete and shows that their morphology has remained largely unchanged over time. However, the size of dragonflies has changed significantly. Their ancient relatives were giants compared to the species that exist today. So, what is it about the dragonfly's morphology that makes it the most effective predator alive today? And if this form is so effective, why did it gradually shrink over the millennia? Why did evolution take away a world of nearly 3-foot-long aerial monsters that once dominated the skies? Odonata means toothed ones in Greek, and the name for these fearsome predators comes from their prominent chewing mouthparts, armed with sharp teeth located under their heads. Dragonflies are also characterized by a freely moving head, very short antennae, large and highly developed compound eyes, minimalist simple eyes, and 2 pairs of long wings. The only difference between extinct dragonflies and present-day ones is their size. Some species from the Paleozoic era had wingspans exceeding 70 centimetres, 27.5 inches, whereas the largest species today only reach a wingspan of 16 centimetres, 6.3 inches. Both males and females can be easily observed perching and flying around aquatic habitats. Part of the reason for this is that dragonfly eggs must be laid in water. They typically feed on mosquitoes and other small flying insects that live in their hunting grounds. Interestingly, dragonflies can eat while flying. Despite being considered a relatively primitive insect, the dragonfly possesses some of the most unique and incredible flight adaptations of any animal, allowing it to achieve both high speed and great agility. One adaptation that dragonflies have, which very few other insects possess, is direct flight muscles. Most other winged insects have what are called indirect flight muscles, which attach to the walls of the thorax and deform it as they contract and expand. The deformation of the thorax transfers its resonance to the wings, causing them to vibrate and begin flapping. While indirect flight muscles have their own advantages, dragonflies, instead, have individual muscles attached directly to the base of each of their wings. Being able to control each wing independently allows them to maneuver and control each wing in 3 dimensions, meaning they can control horizontal, vertical, and rotational movement. This gives the dragonfly a level of precision and flexibility that most insects with indirect flight muscles cannot match. With this independent control, the dragonfly is one of the few insects that can propel itself in 6 directions: up, down, left, right, forward, and even backward. Another remarkable aspect of dragonfly flight compared to other insects is their ability to flap their forewings and hindwings in different phases, and they can change this phasing depending on the flight maneuvers they want to perform. One technique, known as counterstroking, is when they flap their forewings and hindwings 180 degrees out of phase with each other. This allows them to hover or fly very slowly forward while generating significant lift. To fly forward quickly, dragonflies can use a flight pattern called phased stroking, where the hindwings beat down before the forewings at a 90-degree phase difference. While this produces less lift, it generates more thrust, with some species capable of reaching speeds of over 50 kilometers per hour, about 31 miles per hour. This also, incidentally, makes them one of the fastest flying insects. Dragonflies can also use a flight style called synchronized flapping, where both the forewings and hindwings beat at the same time. This flight style helps them accelerate quickly or change direction easily because it generates a large amount of lift. However, they cannot sustain this flight method for long periods, so they typically only use it when chasing prey. Additionally, dragonflies are capable of flying backward, a rare maneuver among other animals except for some small flies and hummingbirds. They do this by tilting their body up at a 90-degree angle to change the direction of the force generated by their wings. Dragonflies can also choose to stop flapping and glide, using the lift from the air to move. In some special cases, the female may be carried by the male, who uses his wings to propel them both. The ability to switch between multiple flight styles and perform masterful aerial maneuvers is undoubtedly what makes dragonflies such effective predators when hunting flying insects, as well as when evading their own enemies. Dragonfly wings have a prominent feature called the pterostigma, which is a small coloured spot on the leading edge that is heavier than the rest of the wing. The pterostigma acts as a counterweight, shifting the wing's centre of mass forward relative to its axis of torsion. This helps prevent an undesirable oscillation known as flutter on the leading edge of the wing when the dragonfly flies fast. Without the pterostigma, a dragonfly's wings would be prone to vibrating, affecting its ability to glide at high speeds. This phenomenon is not only dangerous for dragonflies, but also affects larger man-made structures like airplanes and buildings. And it was the cause of the 1940 collapse of the Tacoma Narrows Bridge. For the dragonfly, this small spot, which accounts for less than 0.1% of its total body weight, allows it to achieve 10 to 25% faster flight speeds than it would without this feature. Dragonfly wings are not completely flat surfaces. The wing veins create three-dimensional corrugations that improve flight efficiency. These veins help stabilize the wing and prevent deformation due to resonance, allowing the dragonfly to easily adjust its angle of attack and generate stronger lift. But the dragonfly's deadliness comes not only from its speed, stability, and maneuverability, but also from how it sees the world. This is another critical factor that enables it to be such an excellent aerial predator. The dragonfly not only dominates in flight capability, but also possesses incredible vision. Its characteristic compound eyes are the largest in the insect world, consisting of over 30,000 individual lenses, ommatidia. Each lens acts like a tiny telescope, detecting light from the direction it points. Because their eyes wrap around almost their entire head, dragonflies have a nearly 360-degree field of view, perfect for observing their surroundings and spotting potential targets without having to move their body. Each ommatidium contains 4 to 5 opsins, which are light-sensitive proteins that absorb different colours in the spectrum. allowing dragonflies to perceive colours from orange to ultraviolet. This is very useful when they hunt during the day and detect objects through visual cues. With 30,000 ommatidia covering a 360-degree field of view, dragonflies do not have the visual acuity of humans or birds. In return, they're extremely sensitive to movement, and this sensitivity is many times stronger than that of humans. A prey item typically occupies no more than 1 degree of a dragonfly's field of vision before it decides to pursue. This means that movement across just 2 or 3 ommatidia is enough for the dragonfly's brain to detect and process the motion very quickly, allowing it to immediately chase the prey or evade a threat. The dragonfly's eyes also have regional specializations. The upper or dorsal region of the eye is most sensitive to short wavelengths of light, namely ultraviolet and blue. Many dragonfly species fly low over water when searching for prey, which helps potential targets stand out more clearly against the blue sky. On the other hand, the middle and lower regions of the eye are sensitive to a broader range of wavelengths. This likely aids in identifying and pursuing other dragonflies, whether they are potential mates or rivals. Since a dragonfly often approaches from the front or above, it can also help identify stationary prey, like insects caught in a spider's web. This is loot that a dragonfly will occasionally steal from a spider if no flying targets are available. These visual capabilities, combined with masterful flight skills, create a formidable predator. However, it is the way these two factors are integrated that makes the dragonfly the most effective predator existing in the world. It's not just the wings or the eyes that make the dragonfly such a successful predator, but also its brain. The dragonfly's brain is highly optimized for hunting strategies, allowing it to predict where its prey is going, enabling the hunter to move quickly to intercept its victim. The dragonfly's brain not only controls its superior flight and vision, but also equips it with an optimal hunting strategy. Dragonflies use a predictive strategy to intercept prey, rather than simply chasing it. In studies of other predators, such as birds of prey and predatory insects, it has been found that there are two main strategies used in hunting: tracking and interception, with interception being much more difficult to execute. The tracking method is simpler, where the predator keeps the prey stable in its field of view and accelerates to close in. The predator approaches and gradually shortens the distance to the prey until its superior speed allows it to catch up. The interception method, meanwhile, requires the predator to fly along a predicted path to a point where it thinks the prey will be. This is more complex because it requires analysing the position and speed of both the prey and the predator so they can meet at the same time. However, if predicted accurately, this method reduces reliance on an absolute speed advantage, helping the predator save energy by not having to fly as fast or accelerate suddenly. Although dragonflies have enough speed and agility to use a tracking strategy, they primarily rely on interception to hunt. In humans, learning to intercept is a behaviour that needs to be trained. But for dragonflies, scientists believe this behaviour is likely hardwired into their nervous system, directly linking their visual and motor systems. However, when using an interception approach, the prey rarely stays still in the dragonfly's field of view, which makes hunting more difficult. Studies show that dragonflies constantly adjust their heads almost in sync with their prey, keeping the target in the regions of their eyes with higher visual acuity for tracking. In fact, this synchronization is so precise that the movement of the dragonfly's head is not just a reaction, but appears to be a predictive action. This perfect combination of mind and body has helped the dragonfly achieve the highest hunting success rate ever recorded by researchers. In 2012, researchers at Harvard discovered that dragonflies catch about 95% of the prey they pursue. This is an incredibly impressive number for any animal, especially for a flying one. A dragonfly will consume any flying prey that is the same size as or smaller than its head, such as bees, moths, flies, or mosquitoes. Larger species can even catch and eat other dragonflies. But if they are the best predators, why did evolution push them to hunt smaller prey? And why couldn't dragonflies have remained giants with 70 centimetres wingspans, hunting larger prey? There are two main hypotheses regarding the reduction in dragonfly size, and they are not mutually exclusive. The first hypothesis suggests that 300 million years ago, the oxygen level in the atmosphere was much higher than it is today. It is thought that this abundance of oxygen could support larger insect bodies, as they depend on the diffusion of oxygen through small holes in their exoskeletons to breathe. When oxygen concentrations dropped to current levels, the maximum size an insect could attain also decreased. The second hypothesis proposes that around 150 million years ago, as small flying dinosaurs and birds began to evolve, they may have competed with large dragonflies in the same environment. Since birds primarily hunted larger prey, while dragonflies targeted smaller prey, smaller dragonflies faced less competition and had a better chance of survival. Very few insects can match the success of the dragonfly, a species that has existed for a relatively long time and has remained unchanged for hundreds of millions of years. With perfect adaptations that help them maintain their position as top predators, it's no surprise that engineers and scientists are eager to study and replicate the dragonfly's flight and hunting abilities. This impressive insect has become an inspiration for many biomimicry projects aimed at recreating how they track targets and perform acrobatic flight maneuvers. To date, no small-sized drone equivalent to a dragonfly can fly freely in the air. But several prototypes of micro-aerial vehicles are under development. So, the next time you see a dragonfly flying around a pond near your home, take a moment to admire this killer of the skies and be thankful that they are as small as they are today, or at least be glad you're not a fruit fly. While morphology is crucial to the long-term success of the dragonfly, its behaviour and life cycle are just as important. Dragonflies not only dominate the insect skies, but their larvae are also formidable aquatic predators, with jaws that can extend to half their body length. The world of dragonfly larvae is even more bizarre than that of the adult dragonflies we are familiar with, and their hunting strategies are far more terrifying. Are you impressed by this unique insect? Leave your thoughts in the comments below.